All right, so if I want to finish this, what I'm going to say is, okay, if you're in the B group, then I want my prediction to be 20. So if you're in the B group, you're not in the A group. I don't have to worry about that term. But I want to add 5 to the 15 if you're in the B group. Okay, and now just check that it works. So if you're in the A group, then this equation says 15 minus 5 times 1 plus 5 times 0. Well, that's equal to 10, and that's exactly what I wanted for the A group, so that's good. If you're in the B group, this equation says 15 minus 0 plus 5 times 1. Well, that's 20, which is great because that's exactly what I wanted as my prediction if you're in the B group. And if you're in the C group, that means that C is equal to 1, but A is equal to 0 and B is equal to 0. Then this just predicts 15. Perfect. Okay, so that's how you use linear regression. Now note that linear regression and tree give the same prediction in this case of one categorical predictor, right? In both cases, you get 10, 20, and 15, which is exactly the means that you wanted. This works great, okay? I want to note down one concept that's important though, which is that I made a choice. I made a choice right here to use A and B as the categories that I was going to mention. I could also equivalently have said, well, I'm going to tell you whether the person is a first year, that's A. I'm going to tell you whether they're a junior, that's C. And I'll just leave out the category of sophomore with exactly the same logic. If I tell you, if you have a bunch of people who are either first year sophomores or juniors, and I tell you whether they're first years and whether they're juniors, I don't also have to tell you whether they're a sophomore. You can figure it out, right? Like if they are a junior, they're not a sophomore. If they are not a first year or a junior, they must be a sophomore. So instead of leaving out the C, as I did right here, I could also choose to leave out the B. But then I have to write the equation down in a slightly different way because I need to write down the equation so that it's a function of the indicators A and C. So if I do this, all right, well, the first number I write, the intercept, is always the value that I want to predict if both my predictors are actually equal to 0. So if A and C are 0, I'm in the B group, which means my prediction should be 20, okay? And if I'm in the A group, I actually want to be predicting 10. So I'm going to have to subtract 10 from that 20. And if I'm in the B group, then I want to be predicting, if I'm in the C group, I want to be predicting 15, right? So if I'm in the C group, I want to be subtracting just 5 from that 20. So let's stop and check that this works. Okay, so if you were in the A group, then this equation says 20 minus 10, that's equal to 10, that's what I wanted. Okay, if you're in the B group, this equation says 20 minus 0 minus 0, you get 20, that's what we wanted. If you're in the C group, this says 20 minus 0 minus 5 is 15, that's exactly what we wanted. So these two equations are actually equivalent. These are equivalent regressions. These are equivalent models. These lead to exactly the same predictions. They're just in terms of different levels of this categorical variable. These are interchangeable. You might have reasons for doing it one way versus the other if you're hoping to, for example, do some hypothesis tests about the number you write before A, for example. Then you want to make sure that A is actually in there. And we'll talk about that kind of idea more as we go forward. So there can be reasons to choose between either one of these in terms of what comes out of your model output. But in terms of the model itself, these are the same model. They're interchangeable, they're equivalent, they make the same predictions. And going from one to the other is called reparameterization. So you'll hear people say, should we reparameterize? And it's called that because you're changing what the parameters in your data set are. The number you write before each variable is called the coefficient. So in the first model I've written here, I have an intercept, I have a coefficient for A and a coefficient for B, and those are my parameters. In the second equation I wrote here, I have an intercept, I have a coefficient for A, and I have a coefficient for C, and so I have different parameters, right? Those are my parameters, and I have redone them, I reparameterized. So what I want you to see right now, though, is that these two equations are identical in terms of the predictions they make, and it's your choice which one to report. The next context we'll think about is one continuous predictor, and we'll look at a few different ways that one continuous predictor might look. Okay, so here's one example. So here's X. X is continuous now, though, so it's not what class year you are, but something more like your political view on a scale, something like that. Okay. And Y is still going to be a variable like this. It can be equal to 10, it can be equal to 20. And let's suppose, I'm just making it up, the data looks kind of like this. So I'm trying to draw this, and you should draw it in your notes as well, so that when X is negative, the Y values are right around 10, and when X is positive, the Y values are right around 20. Data can look like that. That could totally be true. Okay. So let's think about what each of our methods would do. A spline would do a connect the dot. Okay, that's my spline. That works pretty well for the flat parts of this, but it's a little weird around 0, right? Like, because it has to be a curve, if you get, if you have a number right below 0, right above 0, it's kind of giving you a number that's in between 10 and 20 instead of right at 10 and 20. So it's not perfect. That's what that'll do. Okay, what about a tree? Well, let's try to make a tree. Okay. Well, if I have to split this data into 2 groups based on the predictor, think about it for a moment in your mind right now before I say it. The most obvious value of X on which to split this data into 2 is 0, right? So X could be positive or X could be negative, and I should put a less than or equal somewhere, so I'll put it there. And so if I want to use my tree to make predictions, well, if X is positive, it looks to me like the best guess at the mean of Y should be 20. And if X is negative, it looks to me like the best guess at the mean of Y should be 10. Okay. That's my tree. And so I'm going to try to draw my tree prediction onto this graphic. And this is important. This is the place, this idea of drawing the tree prediction onto the graphic is the place where I want you to see how regression trees give predictions that do relate or can be compared to what you get out of something like a linear regression. So, okay, what does this model say? It says that when X is negative, my prediction is 10. So I'm going to draw a horizontal line at 10 for all the negative values of X. That goes all the way to 0. And then when X is bigger than 0, right, open circle if I want, I get a horizontal line right there. That's my tree in green. Okay. So the tree prediction in this case is exactly what the data looks like, right? If it's negative, it predicts 10. If it's positive, it predicts 20. That's how I drew it. Okay, so that's pretty good. What's a linear regression going to do? Well, if I try to make my linear regression a function of X, I'm going to have the mean of Y given X is equal to, well, some number, some intercept, plus some slope. And I'm now converting, instead of just using numbers, I'm using the conventional notation for this. Beta naught for the intercept, beta 1 for the slope. The point is I'll draw a continuous line. Well, if I try to draw a line through these dots, it doesn't look so awesome, right? There it is. This is my linear regression. That doesn't look so good, right? It's usually not equal to 10 or 20. It kind of zooms past them. It's usually some other number above or below. So I'll say something else about the linear regression in a minute, but what I want you to see here is that the way I drew this picture, right, the tree wins. Tree is best if the data looks like this. Because what the tree does is it discretizes the Y values. But if a tree has 1 split and therefore 2 nodes, the tree is only capable of giving back 2 possible numbers as the predictions. But if the data looks like the data I drew here, whether it's always right around 10 or right around 20, then a tree is the perfect way to summarize that data. Whereas a spline or a linear regression are going to try to make the Y values more continuous, more connected than they really are. Before I show you a different example, let me just say, because students, if we were in a live class, I think one of you would have your hand up right now saying, wait a second, isn't there a way to write down a linear regression that would summarize this data well? And there is. The way to do it is to make a new variable that's an indicator for whether X is positive or not. So you can make a new variable, so call it I, that's equal to 1 if X is positive, and 0 if X is negative. And if that's the case, then you could write down that the mean of Y given X is equal to some value beta naught plus some value beta 1 times I. Because essentially what we've done now is we've converted this back into the case on the first slide where I said 1 binary predictor. So here you can even give these values. This is going to be 10 plus 10 times I. We're just back to the original case. So this one is equivalent to the tree. Right, but the first one I drew here is not equivalent to the tree if you actually consider X continuous here. Okay. So this scenario, we have this flat lines, is perfect for a tree, or if you want to create a new variable that is an indicator for different regions of X, then sure, that could work as well. We're still going with the one continuous predictor, but I'm just going to draw a different picture this time. Okay. And actually, I want you to describe it before I go on. I want you to think about it. So if I have X and I have Y, I'm trying to draw an example now where the spline wins. So I want you to think about for a moment, what does this data have to look like if I want the spline to be better at making predictions than the tree is, and also want the spline to be better at making predictions than a linear equation could be.